Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. In this video, we will discuss about histogram equalization. First, I will try to give an intuitive idea about what it means and what is the basis for histogram equalization, and then we will do the mathematical treatment of histogram equalization. So let me move on to the notebook mode for this purpose. Before going into histogram equalization, let's take a look at one of the image enhancement method that we have already discussed, particularly the contrast stretching method. In that method, what did we do? Assume that I have a distribution of intensities there. For example, let this R be different possible values of that could be there from 0 to L minus 1, and then we are plotting the histogram there for a given image. Let's call that image as I of x comma y. Let the minimum and maximum intensities in the given image be I min and I max, giving you the range of values there. So if you point them out in this histogram, this value then in that case would correspond to I min, and this would correspond to I max. Then we have our own definition of what it means by an enhanced image. Let's call it qualitatively as good image. We had our own definition of what is a good image. What is our definition when we are using contrast stretching? Is the image where the intensities gets distributed over the entire image. The intensities are distributed over the entire range. How did we achieve that? For example, we then wanted the minimum value to go to 0. So what we did then, I of xy, minimum value that was there is I min, so that we wanted to go to 0. So I of xy minus I min would bring it to 0, and that also subtracts, when we are subtracting throughout the image I min, the maximum value would now become in the modified image I max minus I min. Okay, so this would give you, when you hit I of xy equal to I max, this whole fraction would give us one value, and we want it that 1 to go to L minus 1. So this whole thing is multiplied with L minus 1, so that that would get mapped to L minus 1. And then of course you do a quantization, or you approximate it to the nearest integer, and that is what is giving you a new image after applying this transformation on the image. Now we are coming up with another assumption now when it comes to histogram equalization. Let's again make the same question: what is a good image? The earlier definition of what is our good image has given us a contrast enhancement. Now we are assuming that when we have a good image, then you have histogram is equal. That's what we roughly mean here when we say it's a good image. What does that mean now? Let's say I have a distribution here. Okay, some distribution is there. Let me call this value as R, varying from 0 to L minus 1. Assume that there are 100 pixels in a given image. So if you, for example, order them in the increasing order of intensities, by the time you come to 50% of the pixels, you are somewhere in the middle of this histogram. In other words, while we are dealing with contrast enhancements, we are not concerned about absolute values of or the distributions that you observe here in the y-axis of your histogram. You are just looking at the range of intensities that you could have. Now you have slightly expanded your definition of a good image by saying that number of pixels that are having a particular intensity value, that number, that frequency also, you are giving it importance. So that's how you are going to define your histogram equalization transformation. Anyway, we will go into a rigorous mathematical approach a little later. Before that, let me write you some intuitive expression for this. Let the earlier value be R. Now you want to apply a transformation on this R that gives you a new value of S that should give you more or less equal distribution of your histogram. By the way, all the histograms that we are drawing here are the normalized ones, where you are dividing the number of pixels having that particular intensity by total number of pixels and thereby resulting in a PDF. Now let's write an intuitive expression for this S equal to T of R. I is varying from 0 to R. Then, as I mentioned, this is a probability density function, a discrete equivalent of a probability density function once you divide it with total number of pixels. So let's call this as PR of R, your x-axis being R. This is the probability density function PR of R. So this PR of I, if you are doing it, what would happen now? Take a look at this. So this essentially would give you the proportion of pixels that are having intensities up to R. Then you multiply the whole thing with L minus 1 here, that's being the maximum value. Now see what would happen. Assume that you are half the way. Okay, total number of pixels PR of I, this whole sum, okay, density is giving you for that particular intensity. So number of pixels that are having that particular intensity are less than that when it comes to 0.5. So this would get mapped to L minus 1 by 2, somewhere in the middle, right? And then when you reach the maximum value here, L minus 1 for example, the sum would go to 1. So that would get mapped to L minus 1. Okay, so hope it is clear to you from this definition on why we are expecting this function to give us, in theory, an equal histogram. However, you could notice here the S values that would be getting here with this transformation will not be an integer value all the time. So that is when you will be approximating it to the nearest integer, and that could eventually result in a transformation which is not exactly equal but somewhat better than earlier and somewhat close to the equal histogram. We will see that soon with some examples. Hope this idea of histogram equalization is clear to you. I summarize here again. The assumption here is that when you have a good image, in that the histogram values would be more or less same for each intensity value. With that, you could see here, if you are defining a transformation like this, where from R you are moving to S, and then suppose the assumption now is that you could, this being S, the new probability density function for this S is what you are getting now. That's, let's say, more or less well distributed. Okay, that's our assumption. In practice you will not get it exactly. One of the reasons being this function could result in a non-integer value, so you need to approximate it to the nearby integer values. Now let us try to analyze the same thing mathematically by starting from a continuous case. What is it that we are given here? Initially your variable is r. The r could vary from 0 to L minus 1. These intensities you are mapping to a new variable s. We also assume here that inverse transform also exists. By that we mean r you could get all the time, okay, T inverse of s, which means your mapping function is strictly monotonical. And also we know that for a given r value, the PR of r is a probability density function, and then S also result in a probability density function here. From the basic probability theory, what we could say now about P probability density function of the new random variable S, this is equal to probability density function of R multiplied by absolute value of dr by ds. This is the basic result, and these two are related, one is obtained from the other, and there is this inverse relation existing between them. Then this is how the probability density function of random variable r and the transformed variable s are related. Okay, now let's start with a special case here. Let be this function be s is which is mapping transforming r be L minus 1 multiplied with, you want to find out this function for a given r, so you integrate from 0 to r for this probability density function that you see here. And let's use a dummy variable here, w d w, which means let's say you want to compute for this value r naught, you integrate it till here, right, and then multiplying it with L minus 1 is how we are defining our s value. This is a special case we are assuming for s. The question we are trying to now answer is, what is the probability density function for this random variable s? This is what we are going to answer now. How do we get that? We know, for example, PR of r. So if we know dr by ds, you could get ds of s here. So how could you get that? Let's say there is a variable s we have defined. So let's take the derivative of this with respect to r. What are we going to get there? L minus 1 is anyway constant, I can take it out. So d by dr of integration from 0 to r probability density function of dr of omega into d omega. And again, a basic fundamental result in calculus, if you are integrating with respect to r, the integration is from 0 to this r, and then dummy variable of omega you are doing it, this would be equivalent to PR of r. So this derivation and integration in a way cancels out intuitively, and this would be eventually would be equivalent to its value computed at r. So what do we get here? ds by dr is equal to L minus 1 into probability density function at computed at r. Equation number 3. Now we want ps of s, so you absolute value of dr by ds, you know ds by dr, so take inverse of it and substitute there. So substituting equation number 3 in equation 1, what are we going to get there? Probability density function ps of s is equal to pr of r into absolute value of dr by ds, so take inverse of it, which would be then equivalent to L minus 1 into PR of r. So these two are getting cancelled for any given value of r. So what are you getting as the probability density function here is 1 by L minus 1, the most important result here. Notice here, irrespective of what is the probability density function for PR of r, once you are using a cumulative CDF here multiplied by L minus 1, for that random variable, the PDF is always uniform. So if you want, let's plot this PDF of it. You have random variable S varying from 0 to L minus 1. Independent of S value, you always have this magnitude equivalent to 1 by L minus 1. So now that means it is uniformly distributed, right? So this is the case when you have a continuous parameter. But now what we have in case of a digital discrete image is that you don't have the integration here. That's the summation. You have its value. We need now a discrete equivalent of a PDF. So let's write that function for a discrete equivalent. Now what do we have here is s equal to this equation 2. You want to consider a discrete equivalent of it, since this value is there only at integer values of omega. So that would be summation. Let me use here a variable I varying from 0 to r, then PR of I, right? That's all. PR of I. This would be the new transform function, and you could see here the continuous equivalent of it is a uniformly distributed one. But when the moment you move it to the discrete domain, the resulting transformation need not always result in a PDF equivalent which is uniform, because you are going to map those which are there at non-integer to the nearby integer values. But nevertheless, that's the best you could do, right? I hope now it is clear to you regarding what's the transformation that you need to apply to a given image in order to obtain a discrete equivalent of it. All you need to do is, for example, now this is very easy to implement it. Okay, let me quickly show you something here. You have, for example, some transformation here, okay, 0 to L minus 1. So if you want to compute for a given r to which it gets mapped to, if you want to find out, for example, this one to which s value it gets mapped to, if you want to find out, all you need to do is sum up from 0 to this r naught, all these values of these PDFs, you sum it up, then multiply it with L minus 1 and approximate it to the nearest integer. That's all you have to do. The implementation of histogram equalization is very simple. Hope it is clear. Now let me switch back to the slides mode where we will see some illustrations and more details. Yeah, this is what we have done now. S equal to transformation T of R, and we did the derivation where you got a uniform distribution now. Okay, the discrete case, now you need to approximate it to the nearest integer, which means let's say you add to the resulting value 0.5 and take floor of it. It's just an implementation detail. Okay, or you could say it is like equivalent to saying if you get 4.6, let's say, then you make it to 5. If you are getting 4.4, you make it to 4. It's as simple as that. However, as you are doing this round off, and also because of few other reasons, perfect equalization as such is not possible here. Let's see a worked out example here. Assume that you are using a 3-bit representation for storing the pixel intensity values, which means you could have values from 0 to 7. So that's what you are seeing here. R values are varying from 0 to 7. Now assume that you counted the number of pixels that are having this particular intensity value. So for example 790, 1023, 850 and so on and so forth. You divide it by total number of pixels. If it is having m rows and n columns, you divide with m multiplied with n and you end up with this thing. Now how do you compute the s values here? You would compute s value by L minus 1 here is 7. Let's say I want to compute this value for where this 0 is getting mapped to. So what I would do then, I would go just 0, I would take that I sum up probabilities till then, so that is equivalent to 0.19 here. So 0.19 multiplied by 7, that would give me 1.33. so the 0 value now gets mapped to 1 here. Similarly, suppose I would like to see where this r equal to 1 would get mapped to. Now what I need to do, 0.19 plus 0.25, you sum them up, multiply it with 7, you would be getting 3.08. Then the nearest one is 3. I want you to pause your video here, take pen and paper, and please work out. You have everything that is required here to work out yourself and see whether you are arriving at these values or not. If you want me to keep r values also here side by side in another column, that would be 0, 1, 2, 3, 4, 5, 6, 7. So now 0 is getting mapped to 1, 1 is getting mapped to 3, 2 is getting mapped to 5, and 3 and 4 are getting mapped to 6. Notice here, because of this round off errors, right? Similarly, the last 3 digits are getting mapped to 7. Now with that, you could also realize here that number of peaks or number of values that you would be getting could also reduce here as you are applying a histogram equalization. This is the same illustration in the graph. So you have r here, this is the probability density function, you have it. Now after that, what you are doing here is you are computing sk values. This is giving you non-integer values to which it is getting mapped to. Now what you will do, approximate it to the nearest integer, right? Suppose 0 is getting mapped to 1, right? And now there is no 2 here. The next is 1 is getting mapped to 3. So whichever you have here, around 0.25 for 1 would now come to 3 here. Similarly, let's see the last case here. You could interpret in similar lines for the rest, but let's see the last case here. So 5, 6, 7, all of them are getting mapped to 7. In between 4 is not there here, but these 3 put together, 5, 6, 7 are getting mapped there. So you 5, 6, 7 you sum up, and that's what would come here. So you could see it is well spaced, and wherever you have peaks now, there are more or less equal. Hope this is clear. Another example of, let us see now in terms of previous examples and see how, what is the kind of job this histogram equalization is doing you. This was either from the image or from the histogram. You could easily say that this is a dark image, and on that you are applying histogram. So this would end up something like this. Okay, now how the transform would look like if you are plotting r on the x-axis and the transformed intensity value s on y-axis. If you would like to see, that would be something like this, as marked here by 1. Notice here the range of values that it is having is on the dark side here, so that's where you have a steep slope here. So that itself is getting mapped. By the time you are coming to, let's say, around 64, that value is getting mapped to 255. So this is the kind of transformation that you would obtain between r and s. So, and then if you plot the resulting histogram, this is how it looks like. Now take this image now, that's again a light image where the intensities are on the right hand side. So how do you expect the graph? So it should have a very steep slope on the right hand side at the high intensity values. Till then all these values could more or less could map to 0 itself. So you expect a graph like this. Let's see if that is the case. Yes, that's the case. So this, for example, around 128, a little higher than 128 is getting mapped to 0, and then there is a steep slope here, and 250 you are getting mapped to somewhere around here, okay, close to 255. Then let's see the third case here. You have it in between. Now what should happen? Your curve should have a steep slope in the middle intensities and should have a almost flat slope on either sides of it. Is that not the case? Yes. So all these intensities are getting mapped to 0, and this is something that's getting mapped to 255. And the last example here, this is a very well distributed histogram already. So even after applying histogram equalization, there is not much difference. The same thing you could see here, this is having more or less 45 degrees angle it is there, and there is no steep curves anywhere except there are some adjustments here and there. So that's the effect of applying histogram equalization in enhancing the quality of the image. I repeat, the assumption we are making here is that a good image is the one where you have, if you plot the histogram for it, it will have more or less equal distribution. That's all for as far as the histogram equalization is concerned. I'll just leave you with some questions here which I want you to ponder over, and maybe we will discuss them in the next class. One question is the plot for R versus S. Okay, you are plotting R on the x-axis, the transformed intensities on the s-axis. What is the nature of this plot? Is it monotonically increasing, monotonically decreasing, strictly monotonically increasing, or strictly monotonically decreasing, or none of the above? Okay, I'm sure you know what it means by monotonically increasing and strictly monotonic curves. Otherwise, you just refer to that and check that. So once you figure out what is the nature of these transforms you would be getting with histogram equalization, what is its impact of it? Okay, so that you think about it. Now another question is, here we are assuming that I have equal distribution in the histogram, right? Everywhere more or less you have bars with similar height. Suppose if I a priori know what are the intensity distributions to expect in a given image. Consider a medical image case where I am looking at a particular region in an MR image. Since all anatomies of different people could be similar, assume that I know what to expect in that region, and for some reasons I got a bad scan in the sense still content is there, but in terms of the contrast it is not so good. But having the knowledge of the how the intensity distributions could be, can I modify this existing histogram in a way that this histogram would be somewhat closer or similar to my a priori knowledge of how the histogram should look like? Okay, the hint here for you is, can you use histogram equalization somehow to bring these known a priori information about histogram as well as the histogram coming from the existing image into the same space? Okay, that's one hint I give you. So ponder over these two questions, and also I request you to work out the example by pausing the video at the earlier slides about how R is getting mapped to S. Okay, and see you in the next class. Thanks for watching. Bye. Take care.